ma'am. Monday we have. Is it possible to do it in Tuesday evening, ma'am?
Tuesday evening, like from 6 to 7?
Yes, ma'am.
Okay, fine. Then Tuesday is what's the date? It's 8th of March, right? Fine. Then we'll have it on 8th of March from 6 p.m. 6 to 7.
Thank you.
I'll post in the group again. So let's start today's class. I hope people will join soon enough.
Yes, ma'am. I'll message them to join.
Yeah, just message them and let's start. And okay, so in the last class we were discussing about how to find out the stability of a control system. So as we all know that the stability of the control system, it will depend on the location of the poles of the closed loop system, right? So if your system is stable, or for your system to be stable, you have to the poles of that system should always lie in the left half of the S-plane. If any of the poles they are lying on the right half of the S-plane, then we'll say that the system is unstable, right? So in order to find out stability, so the first step it might seem is that we have to find out the roots of the characteristic equation. So the roots of the characteristic equation is basically the poles of the closed loop system. Okay, so now in order to find out the roots of the characteristic equation, obviously if you are dealing with a higher order system, then simplifying or factorizing that high order polynomial, that becomes difficult. So that's why there is this solution which was provided by Routh-Hurwitz, and using this Routh-Hurwitz criteria, you can find out information about the absolute stability of a closed loop system without actually solving for the roots of solving for the poles of the system. Okay, so we were so in case of Routh-Hurwitz criteria, we saw that there are like two cases or two special cases where the Routh-Hurwitz criteria, the Routh array can become there can be a break in the Routh array. So the first case was if the first element of any of the row becomes equal to 0. That is the first case, and we had seen that in those cases, what we do is that we replace the first the element which is actually 0. We replace it with a very small with a value epsilon, or with a variable epsilon, such that the value of epsilon is tending towards 0, and then we move on with completing the Routh array, and then finally analyzing the system. Now the second case, this also we have actually discussed, so I just want to show some more examples so that it becomes more clearer to you. So the second special case which might arise while you are analyzing the system stability using Routh-Hurwitz criteria is that there might be a case where all the elements in a single row, they all are becoming equal to 0. Okay, so the moment all the elements they become equal to 0, so then what happens is that the subsequent if you want to compute the subsequent or the following rows, then you will see that all the elements of the next row will also become equals to infinity, will be infinity, because we are dividing while we are calculating each component, we will be dividing with the element in the previous row which is equals to 0. So something divided by 0 will give you infinity. So that means in that case also the Routh-Hurwitz or the Routh array, it breaks down. So how to tackle it? So what we do is that in such a case where all the elements in a single row, they become equal to 0, what we do is that we write the equation which is formed by using the coefficients of the row which is just above the row of the zeros. Okay, and that equation is known as the auxiliary equation. Now, once you have written the auxiliary equation, you differentiate the auxiliary equation with respect to S, and the coefficients that you get after division, after differentiating the auxiliary equation, you fill the row of the zeros with these coefficients, and then subsequently proceed with the Routh test. And once you have done with the Routh test, then you see whether then what you need to do is that the roots, so if you solve the auxiliary equation, so all the roots of equal magnitude that will be obtained if you solve the auxiliary equation. Okay, so and if you remember this kind of a situation, like where all the rows of or all the elements of a single row becomes equal to 0, that kind of a condition, it arises or it indicates that there are symmetrically located poles or symmetrically located roots in the S plane. So there might be a pair of real roots with opposite sign, there might be a pair of imaginary roots with opposite sign, or even a pair of complex conjugate roots. So if that kind of a root or a pole combination is present in the closed loop system, then you will get that one row of the Routh array will become equal to 0. Now, if you want to find out what is the value of these roots which are of equal magnitude, then those roots can be found out if you solve the auxiliary equation. So if you make auxiliary equation AS is equals to 0, and from there the roots or the solution of that equation will give you the value of the roots which are of the equal magnitude. And also remember one thing is that the roots of the characteristic equation, they are also actually the same as the roots of the original characteristic equation. And the stability of the system, it depends on the roots of this auxiliary equation AS. Okay. So now let's try to find out. So let's say that you have been given with a characteristic equation which looks like this. Okay, so in this equation, you first of all what you need to do is that you have to check whether the necessary condition is being satisfied or not. So here you see that all the coefficients of these S terms, they are positive. So they are real positive. So that means the first, the necessary condition is satisfied. So now what we'll do is that we'll form the Routh array. Okay, so forming the Routh array is like, so in on the first column, so or rather to the left of the first column, you will have S to the power 6. You will have the terms of S from in the descending order, and then you will first fill up the rows for the first two rows. So the first row will be the odd terms. So the odd term will be this this is the first term, this is the second, this is the third, and this is the fifth term. So 1, 8, 20, and 16. And in the second row, the even terms will come. So the even terms is this one, the second, fourth, and the sixth term. There is no other term. So this will be 2, 12, and 16. So now you see that between, so there is a common factor. So what you can do is that you can just simplify or divide this row with that common factor, so that your calculations, the subsequent calculations, become a little bit simpler. So you divide it with 2, so you will get 1, 6, and 8, right? So now then you subsequently you form the other the next arrays. So for S to the power 4, it will be 1 multiplied by 8 minus 1 multiplied by 6 divided by 1, which will be equals to, or rather in the first, if you don't divide this one, so it will be equals to 1, or rather it will be equals to 2. So in the second case, you will for the second element you will get 1 multiplied by 20 minus 1 multiplied by 8 divided by 1, which is equals to 12. And then the third element will be 1 multiplied by 16 minus 1 multiplied by 0 divided by 1, which is 16. So here also again you can simplify it by dividing it with 2. So you have 1, 6, and 8. Now the moment you compute the fourth row, you see that for the fourth row, you are getting the first term is 0. So 6 multiplied by 6 divided by 1 will be 0. Similarly, since these two rows have the same value, so that means the next row will have all 0 elements. So all the elements in the row corresponding to S to the power 3 is equals to 0. So the moment this kind of a situation arises, what we'll do is that we'll write the auxiliary equation. So the auxiliary equation will be formed by the coefficients of the previous row, which is this S to the power 4. So we'll write the auxiliary equation. So 1 multiplied by S to the power 4 plus 6 multiplied by S to the power 2 plus 8 multiplied by S to the power 0. Okay. So then you will differentiate now. So this is, since it is S to the power 4, so the first term will be this coefficient multiplied by S to the power 4. Had it been s to the power 5, then your equation would have been 1 into s to the power 5 plus 6 into s to the power 3 plus 8 into s, plus if there were some other terms, those things. Okay. So in this case, you have the auxiliary equation. So you differentiate the auxiliary equation and you get 4s cubed plus 12s. Now what you do is that you substitute these coefficients in the row which has all 0 terms. So 4 comes here and 12 is substituted in the second for the second element, right? Then again you can simplify it and divide both the terms by, or both the elements by 4. So you will get 1 over here and 3 over here. And then subsequently you complete the whole route array. So once you have completed the whole route array, you see, then you observe the first column. Okay, so in the first column you see that all the elements in the first column, they have same sign. So there is no sign change in the first column. Okay, so that means your system is system is not unstable. Okay, so we have to find out whether the system is either the system might be stable or it might be marginally stable. So we have to find out what is the actual case. So since there is no sign change in the first column, you can write that the no root of the or no pole of the equation or of the system, they lie on the right half of the S-plane. Now in order to find out the roots which have, or the poles which have same or equal magnitude, what we need to do is that we have to solve the auxiliary equation. So s to the power 4 plus 6s square plus 8 equals to 0. You solve this equation and you will get that there are 4. So the value of s will be plus minus j root 2 and plus minus j2. Okay, so these roots, they are also the roots of the original characteristic equation. Okay, so from here you can see that there are 2 pairs of complex conjugate or you can say 2 pairs of imaginary roots which are present in the system. And if you remember that if your system has imaginary roots, or if the poles of the system, they lie on the imaginary axis, then the system is marginally stable system. So from here, depending on what is the position of the roots of the original characteristic equation. So since here we have imaginary roots, so we'll say that the system is marginally stable system. Now if for some other case, if let's say the solution of this auxiliary equation if it gives you a pair of complex conjugate roots, so and depending on the complex conjugate root, let's say everything is lying on the left half of the S-plane. So in that case, you will say that since if the solution or the system has a pair of complex conjugate roots and all the roots or all the poles, they are lying on the left half of the S-plane, then the system is stable. Okay, so depending on what is the depending on the equation or the characteristic equation which is provided, you have, after solving or after making this route array, you can find out what will be, or you can comment on the absolute stability of the closed loop system. Okay, so now can we find or can we get any kind of information on the relative stability of the system by using Routh-Hurwitz criteria? So relative stability means the degree of stability. Right, so degree of stability as in, let's say from how far from the imaginary axis is the real pole or real part of the dominant pole. So if we know that if the pole is on imaginary axis, then the system is marginally stable. If the pole is on the left half of the S-plane, the system is stable, and if the pole is on the right half, the system is unstable. So if you want to find out the degree of stability, you have to find that how far from the imaginary axis is the real part of the dominant pole. That will give you information about the relative stability of the system. In order to find out, or in order to get information about this relative stability of a system using Routh-Hurwitz criteria, what you need to do is that, so suppose in this figure you see that this is the S-plane. So S-plane means there is zeta over here and this is the j omega axis. Okay, so now for analyzing the relative stability, what we'll do is that we'll move the imaginary axis of the S-plane, we'll shift it by an amount, let's say some value a, and we'll form another plane which is known as, let's say, a p-plane. Okay, so the mapping of this p-plane with S-plane is given by, like, if you have an equation fs, if you substitute s by p minus a, you will get f of p. So the mapping of fs and fp, that is done by this simple substitution, s equals to So S equals to P minus A. This will lead to mapping of. So Fs maps to Fp by this substitution. Okay. So now if you substitute this, then similarly what you can do is that you can find out, you can apply this Raoult's test on Fp, and if after performing this Raoult's test on the polynomial Fp, you find that the roots of Fs, whether they are lying on the right half of the line S equals to minus A. So now this is the imaginary axis, you can say the imaginary axis of the S-plane that has been shifted to the left by an amount of A. Okay, so that means, so now this will be for the P-plane. So this line is your imaginary axis. So if after applying the Raoult's test, you see whether any part or any root of this Fp that is lying to the right of this line. So for this P plane, basically anything which is, if anything is lying on the right half in this region will indicate that the system will have a pole or a root in the right half of the P plane. Right half of the P plane means, so that means the system will be will go to instability. Okay, so then the relative stability can be found out whether depending on whether the roots of Fp, they are lying on the right half of this S equals to minus A, this line. Okay, so and this relative stability of a system, it depends on the settling time of the system, and this settling time is basically, if you remember, the settling time is for a second order system, the settling time Ts that was usually given by that is usually inversely proportional to the real part of the, so this is inversely proportional to the real part of the dominant pole, and the real part of the dominant pole is given by minus zeta omega n. So if your characteristic equation is S square plus 2 zeta omega n S plus omega n square equals to 0, then the roots of this equation was given by zeta omega n plus minus j omega n square root of 1 minus zeta square. Okay, so this is the real part of the roots, and this is the imaginary part of the root. So this value of this of settling time, that is inversely proportional to, you can say that this is inversely proportional to zeta omega n. Okay, so by using Raoult array, what we can do is that we can find out the information, or we can get information about the relative stability of the system. But the problem here is that this is a trial and error method. So what we can do is that, let's say if we want to find out whether the system is stable, or if the roots for the relative stability can be specific. So first of all, the relative stability can be specified by requiring that all the roots must lie to the left of the line S equals to minus A. So that means you will have a margin of 0 to minus A, and this margin of stability, you can say. Now if you want to find out whether the relative stability is dependent on depending on the time constant or depending on the settling time, so you might have to move it depending on the value of this zeta omega n or the settling time. You might have to move it to a different position from minus A to minus B. So, and then again you will have to apply this Raoult's test and find out whether the system is stable or not. So you can say that this analysis of relative stability using Raoult's test, that becomes little tedious, and it is a trial and error kind of a method. So that is not, so mostly Raoult-Hurwitz criteria that is used for obtaining information about the absolute stability of the system. Okay, so now let's try to solve a problem. So in this problem, in this numerical, it is given that, so you have a unity feedback system and the forward transfer function is given by this. Okay, and you have to find out the stability of the closed loop system as a function of k. Okay. So what you need to do over here is that, so this so you can, since it is a unity feedback system, so you can write, so GS is given by this. So if you write the So if you write the value CS by RS, so this will be given by GS by 1 plus GS, right? So your characteristic equation becomes, so that means the characteristic equation is equals to 1 plus GS will be equals to 0, right? So now you can find out this characteristic equation from here. So it becomes S into S plus 4 multiplied by S square plus S plus 1 plus K is equal to 0, right? And if you simplify this, you will get S to the power 4 plus 5 S cube plus 5 S square plus 4S plus K will be equal to 0. So now this is in a polynomial form. So then what we need to do in order to find out what is the stability of the system or how much stable will be the system as a function of K. So what you need to do is that you have to perform the Routh test on this. So for performing the Routh test, so you will first form the this Routh array. So just tell me what will be the elements of this Routh table. So what will be the first row elements of this, of the table?
1, 5.
1, 5. And then there is K also, right? So you have the first term, third term, and this is the third, and this is the fifth term. So there will be another term K, right?
Yes, ma'am.
Okay, and for the second row?
Ma'am, 3, 1.
3?
1.
Where did you get 3? This is the characteristic equation.
5 and 4 it will be.
5 and 4, yeah. There is no 3 term here. So 5 and 4. So then let's try to compute this S square, the elements for this S square. So what will be the values over here? So you will have 5 multiplied by 5 minus 1 multiplied by 4 divided by 5, right? What is that value?
Ma'am,
4.2.
4.2.
4.2. Okay, and then for the second term?
Ma'am, K.
Yes, the second term is K. Okay, fine. Then we'll move on to the next row. So for this next row,
Ma'am, 5K minus 16.2 by 4.
why is it 5K will come first? So you have to multiply this first and then move here and then multiply this.
Yes, ma'am. 16.4.
16.8 minus 5K
minus 5.
divided by 4.2. Right? So you multiply this term with this, then come diagonal A, then move, and then 5 multiplied by K divided by this previous term, which is 4.2. And this term, there won't be any term over here, right? And the last term will be just equal to K, right? And so now if you want your system to be stable, so the condition is that there should not be any sign change in the first column. Okay, so in order to satisfy that criteria, so that means these two terms, this one and this one, should be greater than 0. So the criteria now becomes, so k should be equals to 0, and then there is another criteria which is 16.8 minus 5k by 4.2 should be greater than 0, right? So from here you can find out that the value of k will be equals to, what will be the value of k, or k should be less than?
And 3.36.
3.36. So you can write that the condition for this system to be stable is that the value of k should lie between 3.36 and should be greater than 0. So this is the condition for stability, right? So this first part is done. In the second part, what you have to find out is that determine the values of k for which there will be sustained oscillations in the closed loop. Okay, and then finally you have to find out what will be the corresponding value of the corresponding frequency of the oscillation. So in order to find out, so the moment you have sustained oscillations in your system, so sustained oscillation means the poles of the system will lie on the imaginary axis, right? So the moment you have the poles of they lie on the imaginary axis, so you remember that when in the first special case of this Routh array, so we had or rather in the, so the moment you have the value of k, or you can say that if the value of k becomes equals to 0, so this term is equals to 16.8 by 4.2, and for that other limiting, so you have two limiting values of k, one is 0 and another is 3.36, right? So the moment if you use this limiting value of k, so if the value of k is equals to 3.36, then this row will become, or this element will become equal to 0. Okay, so that means that there is, and this row is equals to 0 means this whole row, basically it has on, this row has only one element. So that means you will have that the so the whole row becomes, the elements of this row becomes equals to 0. So then what you can say is that there must be a pair of you can say that there must be a pair of symmetrical roots which are present in the system. Okay, so now let's find out that what will be the position of that that pair of loop or pair of the roots. Okay, so now you have this value of k. Let's say we put the value of k, we take the value of k equals to 3.36, right? So if we write the auxiliary equation, so that means this term becomes equals to 0, this row becomes equals to 0. So we can write the auxiliary equation as 4.2 into a square plus k equals to 0, right? So the auxiliary equation A is now becomes 4.2 a square plus k is equals to 0. Right, now you just substitute the value of k over here, so you'll have plus 3.36 is equals to 0. And if you solve for this value, so what is the value of s that you get?
Ma'am, 0.8, ma'am, plus or minus 0.8.
Plus minus 0.8. Are you sure you are not missing out any term?
I, ma'am, I will be there.
Yes, there will be a I or j term, right? So that means from here you see that the roots of the auxiliary equation, so these are the poles of the original system, you can say. And these are the same as the roots of the characteristic equation. Right. So here, from here, you see that there is a pair of poles on the imaginary axis. So that means the pair of poles on the imaginary axis, this indicates that the system will have sustained oscillations. So you can say that for this value of A equals to 3.36, your system has sustained oscillations. Now what you need to find out is that you have to find out what is the value of this oscillation. So if you compare this with the previous equation, so this was minus zeta omega n plus j omega n square root of 1 minus zeta square. So if you compare from this equation, or you can write that this is simply equals to, this term becomes, since this is an imaginary pole only, so that means this term becomes equals to 0, the real part becomes equals to 0, or you can simply write that S12 is equals to plus minus j into omega 0, and this omega 0 is basically the oscillation or the frequency of oscillation of your system. So that means the frequency of this sustained oscillation will be equals to omega 0, which is nothing but 0.8 radian per second. Okay, clear? So in a similar way, you can find out, so there are some problems for you to practice at home. So here you have been given with a transfer function. I have given some hints also in order to make it little bit easier or for you to understand or solve the problems. And first, I would suggest that don't look at the hints and then try to solve the problem on your own. In case if you're having any difficulty in solving, then you can look at the hints. Okay, and then the solutions are also given, so you can find out what will be the value of the value of the k and the roots, whatever is needed for this system. So similarly, you can find out there are some more problems for you to practice at home. Okay, so with this we will this Routh-Hurwitz criteria or stability criteria, this topic is over. So now, as you have seen that this Routh-Hurwitz criteria, that is actually providing you only the information about absolute stability, and even if you want to find out information about this relative stability, that becomes a little cumbersome or a very tedious process. Okay, so is there any way from where we can easily find out information about relative stability of a system or the position of the closed loop poles of a system? Is there anything like that? So for that, so as you remember that the roots of the characteristic equation of a closed loop system, they determine the dynamic behavior of the system. Okay, so depending on the position of the depending on the position of the poles and the zeros of the closed loop system, the time domain response of your system will be governed. Okay, so whenever you have, so the main function or the motivation for using a feedback is that using the feedback, what we can do is that we can shift the open loop poles and zeros of the system, and we can shift it in a specific way such that the desired performance or the system performs in the desired way. Okay, but as you remember that the moment you use feedback, there is always a chance that the feedback might lead to instability. Okay, so we cannot randomly use any kind of feedback in any open loop system, in any system. Okay, so we have to choose the feedback in such a way so that the system or the closed loop system that will be generated after using the feedback, that is a stable closed loop system. Okay, so first of all, we need to investigate what is the stability of the closed loop system. So only information, or we need to investigate not only the stability, we need to have information about the relative stability of the system. So having only information about the absolute stability, that is not sufficient. We need to know about the relative stability of the system. Is relative stability as in, suppose we are moving the poles of the after using a feedback, the poles of the closed loop system, they are changing. Okay, so depending on what is my performance criteria that needs to be satisfied, maybe one position of the pole and zero, that is not sufficient. We have to move it to another position. But you never know that the moment you're shifting that pole to another position, how that is affecting the stability of the system. Okay, so we need to know information about the relative stability. So relative stability as in that will affect the peak overshoot, the settling time, all these things. Okay, and this relative stability is directly related to the position of the closed loop poles. Okay, so in order to determine this relative stability using Raoult's criteria, so sorry, this is Raoult's criteria, it is tedious and since it involves trial and error method. So what we can do here is that there is a concept which is known as root locus concept. So this root locus basically it is a graphical technique which is used for sketching the locus of the roots of a characteristic equation in the S-plane as a certain design parameter is varied. Okay, so certain design parameter means, so what our main aim by drawing this root locus plot is that if you have the information from the about the open loop poles and zeros of a system, then and let's say that if you have the open loop poles and zero position. Okay, and now you are changing the value of, so k is the gain, so gain is changed. Okay, so the moment the gain is changed, so if you have a feedback system, so that means the closed loop poles, the position of the closed loop poles will change, right? So now what we are going to do here using this root locus plot is that we will observe that how the position of this open loop poles, or the position of the, or rather how the position of or the path of the closed loop poles that is changing as that is moving as we change the value of a certain parameter. So in most of the cases we are interested in the parameter gain k of the system. So the main concept of root locus is that we will observe the path of the closed loop poles from the open loop pole zero information that is present given to us. Okay. So so this is the main concept of a root locus. So that means that if you have been given with an open loop system, so just by seeing the just by having the information on the position of those open loop poles and zeros, what we can do is that we can find out that how the closed loop poles and zeros will be moving in that S-plane as we change the value of a certain parameter, let's say gain in this case. Okay, so every time we don't need to find the characteristic equation, or for each value of k we don't need to write the characteristic equation and then solve it and find out what will be the corresponding stability. So we can simply find out information about the relative stability of the system from the root locus plot. So we'll come to that in a couple of slides. So this root locus problem that is done for let's say that we are so before going to the root locus thing, so just let me say something else. So let's say that you have a control system designer is supposed to the goal of the control system designer is to achieve a certain desired performance of the system. Okay, so for that what he or she will do is that the location of the closed loop poles, they will be must be adjusted, and they must be adjusted by varying one or more system parameters. So the system parameter can be the gain k, it can be something else also. Okay, so in order to find out the location of these closed loop poles, so the classical methods can be used is that you have to factor out the characteristic equation in order to find out the roots and the pole placement. So that obviously for each and every time they are the parameter is changed, if you have to find out the characteristic equation and then solve it and find out the closed loop poles, so you can understand that it is not a very easy task. Okay, so that is the reason why we are moving into this root locus concept. Okay, so this root locus problem for a single parameter variation can be defined by using this equation. Let us say that if you have been given with an equation or a characteristic equation fs, which consists of which is of this form. Okay, so you have s to the power n plus a1 s to the power n minus 1 till an. plus k into s to the power m plus b1 s to the power m minus 1 till bm. Okay, and k is the parameter which is varying, which is being varied from minus infinity to plus infinity. And all these coefficients like this a1 till an, similarly b1 till bm, all these coefficients are fixed. Okay, so they are not, these coefficients are not changing. The only thing which is changing in this equation is this value of k. And this a and b, they can be the coefficients, they can be real, they can be complex. But generally, when in our interest, we will be limiting our analysis for real coefficients. Okay, so you can say that the locus of, or the loci of the roots when k varies from minus infinity to plus infinity is defined as the root loci of the control system. Okay, so you can, or in other terms, you can say that a root loci is just a generic term. Root loci is the portion of the overall root loci when k has positive value. That is, if you change the value of k from 0 to infinity, the root loci, that is known, the portion of that overall or the complete root loci is known as root loci. And similarly, you can say that complementary root loci is the portion of the overall root loci or overall root locus when k has negative value. That is, when you are changing the value of k from 0 to minus infinity, for that values of k, whatever root locus you get, that is known as the complementary root locus. And if you want to find out the complete root locus or the overall root locus, that is a combination of the root locus as well as the complementary root locus. And you will see that we are mostly, whenever we are drawing the root locus, we will see the values of k, which is varying from 0 to infinity. And simply, if you, so this this complementary root loci, that will be just a, you can say that is a mirror image of this root loci. Okay, so if we are mentioning root locus, we are referring to the locus for when the value of k, that is positive, that is from 0 to infinity. Okay, and there is something else which is known as root contours. So this root contours, basically they are, so in case of root locus, there is only one single parameter which is varying, let's say this value of k. But if you have multiple parameters variable in your system, let's say if you have k and let's say you have some other term alpha, beta, something like that. If you have multiple parameters in your system varying, so the locus of the roots in that kind of a case is known as root contour. Okay. Okay, so now let's see that what are the some basic conditions that needs to be satisfied for drawing a root locus. Okay, so let's say the closed loop transfer function, if you have can be written like this. So Cs by Rs will be equals to Gs by 1 plus Gs into Hs. So that means the characteristic equation is 1 plus Gh is equals to 0, or in other terms you can write that Gs Hs is equals to minus 1. Okay, so the first step or the golden rule which needs to be followed while coming or while drawing this root locus is that, so what you need to do is that the moment you are given with a polynomial, so you divide that polynomial by the terms which do not contain k, right? So in this polynomial C fs, so these are the terms s to the power n till an. These terms, they do not contain the value k associated with it. So the first thing that we'll do is that we'll divide fs with the terms which do not have the variable parameter associated with it. So we can write that 1 plus k multiplied by s to the power m, this thing, divided by s to the power n plus this term will be equals to 0, right? And if you compare this equation with the characteristic equation, you can write that this term is equals to this GSHS. Okay, so you can say that this open loop transfer function. Okay, so remember one thing, that the moment I am saying that the open loop transfer function is equals to GS into HS, that in that case I am referring to a unity feedback system, because in this system, so if this is your G and this is your H, this is your input, this is your output. So you see that this So ideally the open loop transfer function should be equals to G, but the moment you have, if you have a unity feedback closed loop system, so that means G into H is nothing but G. So we can say that this is known as an open, so this value of GS into HS, that is known as the open loop transfer function. And in this case, the value of HS is equals to 1. That is, we are dealing with unity feedback system. Okay, so we can write that, we can say that the open loop transfer function GSHS is equals to this term. Okay, so now here you can write that this GSHS will be equals to K multiplied by some other term, let's say G1S into H1S, where you can say that this G1S into H1S, that is something which does not contain this variable parameter K. Okay, so you can write that, and this GSHS you can substitute it with -1, and you can write from this equation, you can write that G1S H1S will be equals to -1 by K. Okay, so then the conditions which needs to be satisfied are that from this equation you can find out that the magnitude of G1S H1S will be equals to 1 by the magnitude of K for any value of K between this range -infinity to +infinity. And if you want to see the phase criteria which needs to be satisfied is that the angle of G1S H1S should be equals to 2q plus 1 into pi for the value of K greater than equals to 0, where the value of Q is equals to 0, plus minus 1, plus minus 2, they are all integer values. And if you are dealing with K less than equals to 0, that is for the complementary root loci, then the angle condition which needs to be satisfied is angle of G1S H1S will be equals to 2q into pi. Okay, so in practice, whenever we are drawing this complete root loci or this root loci, so what we do is that we have to find out all the points in the S-plane that is satisfying the angle criteria for either K equals to 0 and K less than equals to 0. Okay, so we need to find out the points on the S-plane which satisfies this equation, this angle criteria, depending on whether we are dealing with whether we are varying the value of K from 0 to infinity or from -infinity to 0. Depending on this, if the angle condition is satisfied, then we'll see, then that point will be a point on the root locus, and the value of K along that or at that point will be determined from the magnitude criteria. So the magnitude criteria is G1S H1S will be equals to 1 by K. Okay. In other terms, what you can do is that you can simply write or express this open loop transfer function GSHS in a pole zero kind of a form. So in a pole zero kind of a form means, so you have in the numerator you have K into product of zeros, and in the denominator you have all the product of the for the poles. Okay, so this again you can write that this will be equals to K into G1S into H1S. So if you want to find out the magnitude, so the magnitude of this term will be equals to, so you can write that, so K is not there anymore. If you want to find out the magnitude for G1S into H1S, there is no K term there. So if you know the information, or if you know the pole and zero position of the open loop system, so then you can find out the magnitude of G1 H1S from this equation. So this will be a sum, will be a product of I equals to 1 to I equals to M. The magnitude of S plus Zi, and in the denominator you will have product of J equals to 1 to N and magnitude of S plus Pj. And the condition which needs to be satisfied, that this should be equals to 1 by magnitude of K, and this is valid for all values of K ranging from -infinity to +infinity, right? Similarly, if you write the angle criteria, so the angle criteria will be equals to, the angle would be like the summation of these terms. So I equals to 1 to M angle of S plus Zi minus summation of j equals to 1 to n summation of angle of s plus pj, right? So this should be equal to 2q plus 1 into pi if we are changing the value of k from 0 to infinity, and this will be equals to 2q into pi if the value of k is changing from minus infinity to 0. Okay, so now, so in other words, you can say that for any positive value of k, a point in the S-plane, for example, let's say this S1. So this S1 will lie on the root locus if the difference between the sums of the angles of the vectors drawn from the poles and zeros of GSHS to that point S1 is an odd multiple of 180 degree. Okay, and similarly for a negative value of k, any point will lie on the complementary root loci provided that it is satisfying the condition that the difference between the sums of the angles of the vectors drawn from the poles and zeros of GSHS to S1 is an even multiple of 180 degree. Okay, so this is the angle. So this is basically S plus Zi, S plus Pj. These are nothing but different vectors which are drawn from these poles to a certain point, right? So the angle of these vectors, if you take the summation of the angle of the vectors which are of all these zero vectors, you can say the summation of that minus the summation of the angles which the vectors which are drawn from the poles, if that difference is an odd multiple of 180 degree, then this that point will lie on the root locus. Okay, so let's take an example. So let's say that this is so we have a system like whose open loop transfer function is given by k into s plus z1 by s into s plus p2 s plus p3. So that means this system has 1 0 which is located at minus z1. So let's say this is that 0 minus z1, and it has 3 poles. One pole is at origin, so there is a pole over here. Then there are 2 more poles. So let us say that 2 more poles, they are some complex conjugate poles. Okay, so you have one complex conjugate poles. Let's say P2 is lying over here and P3 is lying over here. Fine. So now how do we, so let us take a random point on the S-plane. So let's say this is the point S1. Now we want to find out whether this S1 that is lying on the root locus or not. Okay, so for this what we need to do is that from all the poles and zeros, we'll draw the vectors from the poles and zeros to that point. So if this is the S1, so we'll draw the vectors from all the poles. So pole from origin, then from pole P2, from P3, and similarly from Z1. Okay, so we have 4 vectors. Now, if the point S1 is a point on the root locus, then the angle criteria should be satisfied. So the angle criteria goes by this, the angle of which this vector which is joining this 0 to this point, that is, let's say this is theta Z1, that minus the angle which this the vectors coming from all the poles they are making to this point. So for this one, for this pole P1, the angle is given by theta P1. For this P3, the angle is, let's say, theta P3. And for this P2, the angle is given by theta P2. And since we are dealing with, we are saying, or the nomenclature that we are following is that positive angle means the angle which is measured in the counterclockwise direction. So if that values, that is equal to an odd multiple of pi, if that equation is satisfied, then we will say that this S1 point is lying on the root loci of root locus. So for this value of k, when k is ranging from 0 to infinity, if this condition is satisfied, so this condition means theta Z1 minus, for this one we have seen that the angle is theta P1 plus theta P2 plus theta P3. If this one is equals to 2q plus 1 into pi for the values of k, for positive values of k, then we say that S1 is on the root locus. Okay, and for S1 to be on the complementary root locus, if we change the value of k, or for negative values of k, if this angle equation is equal to 2q into pi, so then we will say that S1 is lies on the complementary root locus. Okay. So once you have found out, once this angle criteria is satisfied, then what we can do is that we will say that, okay, if this angle criteria is satisfied, that means this point S1 is lying on the root locus. Now in the second step, what we need to do is that we have to find out what will be the value of K for which S1 is lying on the root locus. And how to find out that? For that we need to use that magnitude criteria. So the magnitude criteria will be the magnitude of these vectors, like magnitude of S1 plus Z1 divided by magnitude of S1, S1 plus P2, S1 plus P3. So once if this is, so we know the vector lengths. So let's say if this is A, this is B, this vector length is D, and this vector length is C. So this should satisfy this equation 1 by modulus of K. So that means we can write that K will be, or the magnitude of K will be equals to the vector lengths of the vectors drawn from the poles to that point divided by the vector length of the vector which is drawn from the 0 to that point. So here you can write that it will be, the value of K will be equals to B, C and D multiplied by and divided by A. So then we can say that this point S1 is actually lying on the root locus, and the value of K at that point is equals to, will be given by this equation. Okay, so in a similar way, what we have to do is that we have to select other random points on the S-plane, and we have to apply the same criteria, and we have to see whether that point is lying on the root locus and not. And in that way, we have to find out what will be the complete or what will be the root locus of the, we have to find out the points which will lie on the root locus. But we'll see that we don't actually have to calculate like all these equations for all different points of S1. There are certain rules or which can be followed, and we can draw the equation, or we can draw the root locus by just by simply following those rules. And but the main, yes, I'll just take one more minute and then I'll stop. So so in order to find out, like draw the root locus, we don't have to find out all the points, like we don't have to select all points and then apply this angle criteria and magnitude criteria. If you simply follow the rules which we'll discuss in tomorrow's class, you can draw the root locus, and that rules, they have been designed in such a way that these conditions, this angle condition and the magnitude conditions, they are satisfied. Okay, so we'll continue discussing on this root locus in tomorrow's class. So in case if you have any doubts, you can ask tomorrow, because I don't think we have much time left in today's class. So thank you, everyone.
Thank you, ma'am.
Thank you.